Hey everyone, Katrina here, and today we're going to determine whether three-dimensional lines are skew or not. Be sure to subscribe for more videos and watch to see the full example. So we're first talk about what are the four ways lines in 3 dimensions can intersect. So we're considering this space R3. So that means our vectors are going to have an x, y, and z component. In my previous video, I talked about all the different ways that lines in 2 space, or R2, can intersect. However, in 3 space, we have an extra option. The first option is that our lines are parallel and distinct. So if they're parallel and distinct, that means there's going to be 0 points of intersection. Option number 2, they could be coincident. So what does this mean? This means that there's going to be an infinite number of points of intersection. So for both case 1 and case 2, our vectors have the same direction. So that means that their direction vector is going to be scalar multiples of each other. So we could have, when they're parallel, they have the same direction, but there is some gap in between them. And if they're coincident, then you have the same direction, but then our second vector is going to exist right on top of the first one. So that means that they're going to intersect at every single point. Third, they may intersect at a single point. So intersect at one point. So that means, like I said, we're only going to have one point of intersection. So if we have some vector here, and then we have some other vector, we can see that we have exactly one point of intersection. So this is all the same from lines in 2 space. But what about 3 space? We now have this testy fourth option, where our lines don't intersect, but we also see that they are not parallel. So that's kind of a new concept, is that they can not intersect and not be parallel. And this actually means that they are going to be skew lines. So I want you to hold out 2 pencils in front of you and kind of place them such that they don't touch, but they're also not facing the same direction. So this is hard to draw in 2 dimensions because it's only a 3-dimensional phenomena. So you'd have one vector here, and then maybe in dotted lines, I'll draw this one over. So it's actually hovering above the purple vector in 3 dimensions, but it's never actually touching it. So today we're going to learn how to determine whether our lines are skew or not, because this is a bit of a new skill that we have to develop. So we're going to dive right into an example to see how we can do this. So we have 2 lines which are going to be given in vector form. I'll call it R1, which is, remember, x, y, z, 3 independent variables, equals to 5, -4, -2, plus s, 1, 2, 3. And then our second line, R2, is x, y, z, equals to 2, 0, 1, plus t, 2, -1, -1. Okay, so we're going to go through a bit of a process. So step number 1 is we're going to determine, are they parallel? Parallel, or let's say collinear. So it might be one or the other. So in order to check this, we want to determine if their direction vectors, these ones, are scalar multiples of each other. So let's see that. We have 1, 2, 3 equals to 2, -1, -1. Is there like a k value? Is there such a k so that this can be true? And the easiest way to check that, honestly, is to look at the negatives. And we can see that right away there's absolutely no value we can choose for k to ever make this true, right? If you choose k 1, 2, 3, -4.5, we're never going to have this equality. So that means that we can right away rule out that therefore it's going to be not parallel and also not coincident. Coincident, collinear, I'm just using those terms interchangeably. So that means that we have now two options. We can either have 1 point of intersection, or we can have 0 points of intersection, and if we have 0, then our lines are going to be skew. So now that's what we have to check. So whenever you go through these problems, I want you to follow this logic. It's always easiest to check if they're parallel or collinear first. If they're not, rule those out right away, and let's check the next potential that our lines could be. So if we have a point of intersection, that means that when we equate these lines, we're going to get a real mathematical answer. If they're skew, then when we equate them, we're going to get something that doesn't mathematically make sense. So let's go ahead and try that. We're going to test to see if they intersect. So we're going to test intersection. Okay, so to do this, I always recommend to put it in parametric form. So right now our vectors are in vector form, but we want it in parametric form because that's much easier. Okay, so let's do that. So from our line number 1, we in parametric form, we just take essentially the first coefficient, the first variable in each of the vectors. So we've got x equals to 5 plus s, y equals to negative 4 plus 2s, and z equals to negative 2 plus 3s. So this is line 1, and now let's check line number 2 in parametric form. We have x equals to 2 plus 2t, y equals to 0 minus t, and z equals to 1 minus t. So now what we want to do is we want to equate x's, y's, and z's. And then we want to solve for t and s. Okay, so when we are equating them, we're going to start by looking at the first two equations. Like I said, we're going to solve for s and t here, and then we're going to plug into the third one, and then see if your values for s and t are true there as well. So I'll show you what that means. So let's start by equating them first for the first two, and then go from there. So taking the first two, we've got that 5 plus s equals to 2 plus 2t, and then we have that negative 4 plus 2s equals to, what do we have over here? Equals to negative t. So we can just rearrange the second equation here such that t equals to, what do we have? 4 minus 2s, and then we're going to plug that back into that one. So we've got 5 plus s equals to 2 plus 2 times, we're going to grab our t value over here. So 4 minus 2s. And now we want to solve for s. So what do we get? We have that 5 plus s equals to 2 plus 8 minus 4s. We bring the s's on one side so that we have s plus 4s equals to 5 plus 2 plus 8. So we have that 5s equals to 15. So s, just want to make sure we had all this correct here. 2 plus 2s, brought this 5 over. Oh, sorry, so over here we have 5s. We have to subtract the s over there. So we've got 8 plus 2 minus 5, which is going to be 5. So that means that s equals to 1. And then now we can just plug that back into our t. So then t equals to 4 minus 2 times 1. So t equals to 4 minus 2, which equals to 2. Okay, so let's just summarize what we have there. So we found that s equals to 1, and we found that t equals to 2. So now we want to plug this into our third equation. So our third equation is negative 2 plus 3s equals to 1 minus t. We want to see, does the left-hand side equal to the right-hand side? And that's going to be our test to see whether these values for s and t work. So let's do that. So we have negative 2 plus 3 times 1 equals to 1 minus 2. On this side, what do we get? Negative 2 plus 3, so we get negative 1. We get positive 1. And then on this side, we get 1 minus 2, which is negative 1. So here we can absolutely see that our left-hand side does not equal to the right-hand side. So what does that tell us? That tells us that there is no point of intersection because the values for s and t that we found our first two do not work with our third equation. So that means, therefore, there's no point of intersection. And well, if there's no point of intersection, that means that our lines must be skew because we've already stated that they're not parallel and distinct and they're not collinear, and we just found that there's no points of intersection. So that leaves us to our last final option, that we therefore have skew lines. I hope this video was helpful in both looking at all the different ways that lines in 3 space can intersect, as well as specifically looking for skew lines. If you found this video enjoyable, please give it a like and subscribe for more. I've got plenty more vector videos coming your way, so stay tuned. I'll see you next time.